AP Physics 1 Workbook, Unit 5, Momentum. Activity K, Conservation of Momentum. Remember to pause or rewind the video as necessary. Please read the scenario along with me. Blake is given two carts of unequal mass, little m and big M, and a long track that ensures both carts will travel in a straight line with no noticeable friction. He also has access to other commonly available equipment. The carts do not have any way to connect together when they come into contact. He asks the following three questions. 1. When the two carts collide, is the total momentum of the system conserved? 2. When the two carts collide, is the mechanical energy of the two-cart system conserved? 3. When the two carts collide, is the force M exerted on big M equal to the force that big M exerts on little m? Part A. Outline a procedure that Blake could follow to make the measurements that could allow to answer all of the three questions above. Give each measurement a meaningful algebraic symbol and state what equipment each measurement is made. Draw a labeled diagram showing the piece of equipment. It might actually be helpful to draw the diagram first so that we know what we're working with. Let's actually go down to the bottom here. Well, the diagram would have your track with two carts. The carts would have little cardboard targets or flags, something that the motion detector could read. You'll see that you'll have a motion detector on one end, a motion detector on the other end. You're going to get the two carts to essentially approach each other, collide, and then, of course, they'll rebound off each other. And the motion detector here is going to get the velocity of this cart. The motion detector here is going to get the velocity of that cart. So let's see how this would be done in terms of procedure. Well, what needs to be measured with this right here? Well, the motion detector is going to measure everything. Motion detector will measure velocity as a function of time. It'll create a velocity time graph. And we could do the following procedure. Number one, we could take the mass of each cart using a balance. You could then put on the carts on either side of the long track with the motion detector set at either end, just like you have here. You could then set the motion detectors to record the velocity as a function of time and then push each cart towards each other, like this. Then, as the carts approach each other, collide, and move away from each other, the motion detectors will send information to the computer to generate velocity as a function of time for each cart. Part B. 1. Explain how the measurements made in Part A can be used to answer the question. The mass has been measured and recorded. If the momentum is conserved in the collision, then the momentum before the collision should equal the momentum after the collision. The motion detector can create a graph of the velocity as a function of time. The velocities of each cart can be measured or can be found before and after the cart, and they can be read off the graph and entered into the following equation for equality to see if momentum beforehand equals momentum after. Part B2. Explain how the measurements made in Part B can help answer question 2. Now remember, question 2 was saying whether or not the mechanical energy of the system can be conserved. Again, the mass has been measured and recorded. If the kinetic energy is conserved in the collision, then the kinetic energy before the collision should equal the kinetic energy after collision. The motion detector creates a graph of velocity as a function of time. The velocities can be found from the graph and entered into the following equation to see if the kinetic energy of the carts before collision equal the kinetic energy of the carts after collision. And finally, B3, explain how the measurements made in Part A can be helped to answer question 3. Question 3 was asking all about is the force that one cart exerts on the other equal and opposite to the force of the second cart on the first one. Acceleration is the slope of a velocity time graph. So again, we're getting the velocity time graph from the reading, from the motion detector. And so if we take the slope of the graph, we can find the acceleration. And mass times the acceleration is the net force that each graph is exerting on each other. So acceleration is the slope of the line on the velocity time graph. The slope can be found by hand or with a computer program. If the mass of each car is multiplied by its acceleration in each case, then the force on m of the force of big M on little m would be equal to the force of little m on big M. AP Physics 1 Workbook, Unit 5, Momentum, Activity L, Inelastic Collisions. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. A dart launcher fires a dart so fast that the speed cannot be measured by any direct method. Angela wishes to determine the speed with which the dart is fired. After being fired, the dart will embed itself into a wooden block. She already knows the mass m of the dart. Part A, Experimental Design. Angela has access to the following equipment. Mark the space next to the equipment that she could use. Well, basically, if she fires the dart into the wooden block, what we can do is we can put the wooden block on a cart that has frictionless bearings. So the wooden block is attached to that. And so basically, if you kind of have a picture of this, you'd have the dart getting fired into the wooden block that's on the cart. And then afterward, the dart block combination, so this is before, this is after, the dart block combination will be able to roll with a particular speed that you can measure. Because this has momentum, the momentum of this is 0, and this will have momentum after as well. And the momenta should be equal because this essentially is an inelastic collision. So what else could we use? Well, we could have the cart on a track. Okay, you could have access to a balance to measure the masses of the cart on the block, because you already know the mass of the dart. And you could, let's see, so how do we get the velocity? Well, okay, to get the velocity, you could use the camera and the video frame by frame, but then you would need distance, so we need the meter stick as well. So those are the pieces of equipment you could use in order to essentially make that process happen. So outline a procedure that Angela could follow. Let's actually take a look at the diagram setup first so that the procedure makes sense. The dart would fire into the block that's on the cart, and then afterwards, the cart and the block would then move. So the dart itself flies into, embeds itself. This would then roll a certain distance, a certain length, right, that the video camera could measure. So the velocity could be measured afterwards like this. So what would need to be measured? Well, we would need to measure the mass of the cart using an electronic balance, the length of the track using a meter stick, and the time that it travels using the camera. So you can use the video frame by frame to get the time. Attach the block and cart. Attach the block to the cart and the mass, and take the mass of the block cart combination and record it as big M. Measure the distance L to the right of the block/cart. Set the block carts on the track. Start the camera. Launch the dart at the block cart. From the video, determine the time, right? And the distance that it moved. So, and of course, repeat several times to reduce error. So then part C, explain how these measurements can be used to actually calculate the speed of the dart. Well, again, remember, this is a conservation of momentum problem, specifically in inelastic collision. So the system is the dart block cart, and there are no horizontal external forces on the system. Therefore, the initial and final momentum are equal. Only the dart has initial momenta, and after they collide, the dart block cart system will all have the same final speed. So this is the conservation of momentum equation we can use to solve for the initial speed of the dart. Okay, solving for the initial speed of the dart, we divide by little m, which is the mass of the dart, and we get the final momentum of the cart block dart system divided by the mass of the little dart, which we already know. Okay, now V final, which is this part here, that can be calculated by dividing the distance that you have you use the video frame. So you can measure L from the video, right? And then you can measure time from the video, right? Because again, there's negligible friction acting on this thing. So the dart block cart should be traveling at a constant velocity after it is hit. So the big M plus little m is the mass of the combined, it's the mass of the dart plus, which you know the mass of the dart plus the mass of the block cart system. So and you can basically find the initial speed this way, and then we can substitute for V final the length that it travels divided by the time it took to travel. And this equation right here would help figure out the mass, or not the mass, excuse me, the velocity of the dart before it collides. AP Physics 1 Workbook, Unit 5, Momentum. Activity M, Collisions. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. A wooden cart of mass big M is set on a horizontal section of a track. The cart experiences negligible friction as it rolls. A dart of little m, which is less than the mass of the cart, is fired with an initial speed v towards the cart, which is initially at rest. Consider the following cases. Case 1, the cart embeds itself in the dart embeds itself in the cart. Number 2, case 2, the dart hits the cart and bounces backward. And then case 3, the dart passes completely through the cart. Part A, for each case, create a pictorial representation of conservation of momentum during the collision. So you can see we're going to create a velocity mass graph to represent momentum. Now, case 1 would be a case where we have an inelastic collision. So let's see how we would represent that. Well, what I'm going to do is I'm going to represent this with, what I'm going to do on this is I'm going to say that each unit is going to be mass M. And I'm going to go and I'm going to shade, let's see, 7 boxes going up just like this. So I have 7 boxes shaded, 7 mass units. So this is going to be the velocity. This is going to be the mass, and the area of that would be mass times velocity, or the momentum. You can see it's 7 boxes shaded. Now the cart has no initial momentum, so make a line across indicating that there's no bar, and that's all the initial momentum. Now if the initial momentum is 7 boxes shaded, the final momentum should be 7 boxes shaded as well. Okay, now how do we do that? Well, the momentum of the dart is only m. The momentum of the cart is significantly bigger. So it's going to be little m plus more. So I'm going to be shading shade 6 boxes over. This right here would include little m plus big M, all of it. But notice I shaded a little bit above this mark. It's not to this mark right here, it's to about this mark right here. So all of this plus that little extra would be, this is what the speed will become. This is the speed, I guess you would call it V final after collision. Okay, and why am I doing that? Because I have 7 boxes shaded here, I've got 6 boxes shaded here, and then 1/7 of a box shaded here, so that all of that little shading adds up to a 7th box. So I have momentum equals momentum. Now in the second case, it bounces backwards, so I'm going to start with the same initial momentum of the dart. 7 boxes shaded. I also start with the situation where the cart has no momentum. In fact, I'm going to go ahead and copy these two for all 3 graphs, because all 3 graphs really start with the exact same initial conditions. It's what happens afterward that's different. Okay, so in case 2, the dart is going to bounce backwards. So what I'm going to do is I'm going to go ahead and bounce the dart backward. It's going to have a little backward momentum. That would be the final speed of the dart. It'll be negative, hence the negative velocity. And then I would have shade this in right. Okay, so now notice what I've done here. There were 7 blocks shaded for that bar graph. There are 3 here and 10 here. -3 plus 10 adds up to 7. This again would be this, so if this is 1m right here, this is just m, this would be essentially, I guess 5m, it would be that much bigger. So it looks like the cart is 5 times more massive than the dart, to at least give you this scenario. And then finally, if the dart passes through, it's going to continue with some forward momentum, but it's going to lose some speed along the way. So there's the final velocity of the dart after collision. But then, remember, guys, I shaded 7 boxes over here. If I have 2 shaded here, that means the cart is going to be moving forward, right, with final velocity v here, and then that's the mass of the cart itself. But I've got 5 shaded boxes, 2 shaded boxes, that's 7 shaded boxes equaling 7 shaded boxes. Momentum is conserved. Part B, create a mathematical representation showing conservation of momentum for each of the 3 cases. So in case 1, momentum initial equals momentum final. In fact, that is going to be the case that we're going to start with for all 3. Okay, now in the first case, the initial momentum is just the dart, mv. Afterwards, it embeds itself in the cart, so mass of the dart plus mass of the cart times v final. V final would be the initial momentum of the dart divided by the sum of the mass and the dart. Now in case 2, the momentum of the dart is the only thing moving beforehand. Afterwards, the dart, mv1 final, moves with negative velocity backwards, and the cart, big mv2 final, moves forward. So if I solve for mv2 final, I have to add this to the other side and then divide by big M. And I get v2 final of the cart is equal to initial velocity of the dart plus the final velocity of the dart divided by the mass of the cart. Now in case 3, we have the initial momentum is just the dart. The final momentum would be mass times velocity of the dart plus mass times velocity of the cart. So that's mv1 final plus mv2 final. And so to solve for v2 final again, I'm going to subtract the final momentum of the dart and then divide by the mass. So v2 final would be equal to the initial momentum of the dart minus the final momentum of the dart divided by the mass of the cart. Part C. Rank the cases in terms of the distance up the incline that the cart travels after the interaction with the dart, and explain your ranking in terms of conservation of momentum and conservation of energy. Well, the farther you go up the hill, the farther you go up the incline has to do with your speed. So let's go back to the picture. Okay, so what happens here? You're going to have a speed v final after collision. The faster the speed, the more kinetic energy you'll have as you go up the hill. The more kinetic energy you have, the more gravitational potential energy you'll have, which means the higher you go up the hill. So which one has the greatest speed after collision? Well, you can see that the one with the greatest speed is going to be this one right here. You're dividing by less and you have a greater numerator. So case 2 is going to have the greatest speed. Case 1 is going to have the next greatest speed because you do have, a decent numerator. You are adding less, but what makes case 3 the lowest is the fact that by subtracting in the numerator, you have a smaller numerator. Even though you have a smaller denominator, you have a much smaller numerator because you're subtracting from the momentum of the dart instead of adding to it. So here it's the momentum of the dart plus the sum of the masses. Here it's the momentum of the dart minus the final momentum of the dart, right? So you're subtracting from it, making it smaller. So I would say the ranking would be case 2, then case 1, then case 3. And just to kind of explain that reasoning, the larger the velocity of the cart post-collision, the more kinetic energy the cart will have, meaning the higher it can go up the ramp, converting kinetic energy into gravitational potential energy. As shown in both mathematical representation and momentum charts, the cart will have the largest post-collision speed in scenario 2 and the smallest post-collision speed in scenario 3. AP Physics 1, Unit 5, Momentum. Activity N, Center of Mass Motion. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. 2 blocks of mass m, 1 kilogram, and 4 kilograms are placed in contact at the center of an 80-meter-long track that exerts negligible friction on the blocks. Both At both ends of the track, there are strips of a rough surface of equal coefficient of friction 0.5. A small explosive charge between the blocks propels them apart at time t equals 0, so that the 1 kilogram block moves with a speed of 40 meters per second along its frictionless track. Okay, so we're given the initial speed of the 1 kilogram block. Well, actually it's the final speed after explosion, but it's the initial speed of its motion. Part A, calculate the time of the 1 kilogram block reaches the rough surface and the time the 4 kilogram block reaches the rough surface. Explain verbally your calculations. Okay, so let's start with the 1 kilogram block first. To begin with, during time on the smooth surface, we start with the equation position as a function of time. X equals x naught plus v naught t plus 1/2 at squared. Since there is no net force on the block because it's sliding on a frictionless surface, we can cancel out the acceleration portion and the initial position is 0. And so we end up with x equals v naught t. And when we plug into that, negative 40 is the position of the block. And when it reaches the end right here of the segment when it reaches the rough segment, it will be at negative 40. And the time it takes to reach that, you're going 40 meters per second, right, in the negative direction. So negative 40 meters per second is the velocity. Divide by negative 40 by negative 40, it takes 1 second for the 1 kilogram block to move this distance right here. Now, the 4 kilogram block. We start with the same idea, but this time, since we're going to start with the idea that during the explosion, there are no net forces. So we're going to start with conservation of momentum. Momentum is conserved during the explosion since there is no initial momentum with 0. So the initial momentum is 0, and that means the total momenta, the momentum of the first block 1, is going to be the same as the momentum of the second block. And the final velocity of the 1 kilogram block was for negative 40, if you remember. That was this right here. And we're needing to use conservation of momentum explosion here to find V2, the velocity of the 4 kilogram block. So solving for V2, we would add the negative 40 over to this side and then divide by 4, and you can see that the velocity of the 4 kilogram block must be 10 meters per second. Now, once we know that, we can now use the kinematics formula. The 4 kilogram block moves at a constant speed. Again, the acceleration part is 0. And plugging in, it's going to move 40 meters to its rough surface to the right at a rate of 10 meters per second. So if you divide the 10 by the 40, it'll take 4 seconds to reach the rough surface. Part B. Both blocks have the same magnitude of acceleration while sliding to the rest of their respective rough surfaces. Calculate this acceleration and verbally explain your method. Well, let's start off with the idea that the net force is equal to mass times acceleration. This particular net force will be friction. Friction is what's going to slow down the object, basically. So when both blocks are on their rough surface, friction is going to be the thing that reduces their speeds. So friction is the reason for acceleration. So your net force is going to be friction, and that's going to be equal to ma. Well, recall that friction is equal to mu times normal force, and that normal force is equal to mg. Therefore, we can substitute mu mg for friction, and that's equal to ma. Cancel out the m's, and the acceleration, therefore, is equal to mu times g. Plugging in, acceleration is equal to 0.5 times 10, which would be 5 meters per second squared. Part C, calculate the time at which the 1 kilogram block comes to rest and the time that the 4 kilogram block comes to rest. Let's take a look at the 1 kilogram block first. On the rough surface, the block slows to a stop, and we can use velocity as a function of time. Recall that the final velocity is 0 because the block is coming to rest. If we solve for time, we subtract the v naught to the left, divide by a, and when we plug in, time is 40 divided by 5, or 8 seconds. So it takes 8 seconds for block 1 to come to rest. The 4 kilogram block, we're going to use the same equation, velocity as a function of time, remembering again that the block is coming to rest, so final velocity is 0. Again, we're going to divide by, subtract v naught and divide by a, and when we plug into this one, this time it's negative 10 over negative 5 because the acceleration is negative, and we get 2 seconds. So it takes, and that should make sense. This block is 1/4 the mass. This block is 4 times the mass. 4 times the mass takes 1/4 the time. 1/4 the mass takes 4 times the time. There's a connection there. Do keep in mind, though, that that's the time that it takes to come to rest, but it had already been moving for 1 second. So the 8 seconds plus the 1 second that it was moving on the frictionless surface, the 1 kilogram block is moving a total of 9 seconds. And similarly, the other block was moving 4 seconds beforehand, plus these 2 seconds is a total of 6 seconds for the 4 kilogram block. Argumentation. Now the blocks are exploded apart the same way as before, but this time friction is negligible everywhere on the track. Instead, there is a wall located at negative 80 meters. Upon striking the wall, the 1 kilogram block sticks to the wall. The graph of the center of mass of position of the 2-block system is shown as a function of time. So what are we looking at here? The graph is showing the position of the center of mass of the 2-block system as a function of time. The graph is 0 up until 2 seconds, and then all of a sudden has a constant positive slope after 2 seconds. So in a clear, coherent paragraph, explain these features. Because there are no external forces on the 2-block system for the first 2 seconds, the center of mass system remains at rest. At t equals 2 seconds, there is a net external force, in other words, an impulse, applied to the system by the wall. The center of mass has to remain the same location relative to the 2 masses, namely the ratio of the distances from the center of mass has to be that 4-to-1 ratio we talked about. 4-to-1 ratio in terms of distances, 4-to-1 ratio of masses, 4-to-1 ratio of the time it took to come to stop. So after the left mass has stopped, the right mass has to keep going. The center of mass has to move to the right to keep the ratio at 4-to-1. AP Physics 1 Workbook, Unit 5 Momentum. Activity O, Conservation of Energy and Momentum. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. Angela, Blake, Carlos, and Dominique are performing an experiment involving carts 1 and 2, which are both light and friction in the bearings can be neglected. The students push cart 1 against a spring of force constant K, compressing the spring a distance x from its equilibrium length. Cart 1 is released, collides with cart 2, and sticks. The two carts continue with constant speed v final after collision. The students are tasked with making v final as fast as possible with the following constraints. First, the compression distance cannot be varied. So we're going to basically be pushing back to the same distance. Now, that doesn't mean the stored energy is going to be the same because you can vary up the... well, actually, no. I take that back. The stored energy will be the same because if the x distance cannot be varied, that means 1/2 kx squared is always going to be the same because the k is constant. So constant k, constant x, the spring energy or the total energy before collision will always be the same. The other constraint is that the masses can either be added or removed from cart 1 and 2 as long as the total mass remains constant. So for instance, you could take mass from 2 and add it to 1, or take mass from 1 and add it to 2, but you cannot add mass to both of them or take masses from both of them. The total mass between 1 and 2 has to remain adding up to a constant value. The total mass has to be conserved. Part A, answer the following questions. Explain your reasoning. You may cite equations, but do not manipulate or combine equations as part of your explanation. So after cart 1 is launched, how will the total mechanical energy of the system, spring and M1, change if M1 is large? The total mechanical energy does not change if M1 is large. Remember, the total mechanical energy is based on the spring energy, right, converting to kinetic energy. You have the same spring energy, even with a larger mass, you're still going to have the same total energy. So with a larger mass, yes, you'll have a slower speed, but you'll have the same mechanical energy. Remember, mechanical energy is conserved. So the total energy does not change. Since there is no net work in the system, including mass 1 in the spring, the total mechanical energy remains constant until the collision, of course. Okay, and the total mechanical energy is equal to the spring energy of 1/2 kx squared. The speed of M1, however, does decrease as mass 1 increases, but the total mechanical energy does not change. So the kinetic energy will be the same as that spring energy. Part 2, after cart 1 is launched, how will the total momentum of the system change if M1 is large? Well, now momentum will be affected because momentum is mass times velocity. So if M1 is larger, the total momentum of M1 will be larger. Even though the speed of M1 will be smaller, it will not be proportionally smaller. So momentum of M1 will still be larger if M1 is larger. Okay, again, we can understand this by the kinetic energy given to the block is only based on the spring energy, and that doesn't change. Okay, energy is conserved and does not change, but the momentum increases as the mass increases. Part B, based on one or both of your answers in Part A, explain whether M1 should be large or small to make the final speed v final the fastest. M1 should be large to make the final speed v final be fastest. Increasing the total mass does not affect the total mechanical energy of M1, but it will increase the momentum. and the speed before the collision. This in turn will include, if the momentum is increased, the speed v final after the collision will be increased. Part C. Derive an expression for v final of the combined carts in terms of M1, big M, which is the total mass combined, X, and K. Explain the expression to support your assertions in Part B. Okay, so let's go step by step. 1, the total mechanical energy before the launch of M1 to after the launch remains constant because there are no external forces doing work on the spring cart system. In other words, energy is conserved. The energy in the spring becomes the kinetic energy after the launch. So in other words, the initial energy is the spring potential energy. The final energy is the kinetic energy. So after the speed, M1 is equal to, when you solve for speed, the square root of kx squared over M1. So what you can see here is as M1 increases, yeah, the speed is going to decrease. The kinetic energy might stay constant, but the speed specifically will decrease. During the collision of the two-block system, there is no external forces, so the total momentum is conserved. Conservation of momentum. So the first part of this problem was a conservation of energy problem. The collision is an inelastic collision, and that's conservation of momentum. Well, we just said a second ago it's an inelastic collision, and therefore the momentum of that first object, the momentum of the first cart, M1, is going to be M1 V1, and then it's going to stick to the second cart, so you have to add them, M1 plus M2. And remember, M1 plus M2 is total M, right? Okay, now what we're going to do is we're going to substitute, a little substitution here. We're going to substitute V1 that we got from the previous problem. So remember, V1 this was the speed of cart 1 after the conservation of energy problem. We're going to substitute that for V1 in the momentum problem. And the mass of the two blocks, M1 plus M2, we're now going to substitute for big M. So solving for V final, we get V final is equal to little m1 over big M times the square root of kx squared over m1. Now, what I did here is I put this under the radical, and I did that by making m1 over m the square root of m1 squared over big M squared. And why would I do that? Because now I have all of this under the same radical, and I can cancel one factor of m1. Which is why I have only one factor of n1 here, and m2 I'm just going to move underneath kx squared. And so now the velocity is proportional to the square root of the mass of the first cart. Line number 8 supports my claim, showing that the final velocity of the two-block system is directly proportional to the square root of m1. Therefore, if m1 increases, the final speed post-collision also increases.